Hi, this is an example problem on calculating the de Broglie wavelength for matter waves from chapter 29. All right, so we've got two objects, electrons, an electron and a proton, something that we typically think of as particle, but as we learn in this chapter, any type of object, whether it has mass as these particles or not, can also have a wavelength and exhibit wave properties. So in this case, we're going to have to use the equation that tells us how to calculate the de Broglie wavelength. Now, for a photon, we know that the momentum can be written as Planck's constant over the wavelength, and therefore the wavelength of a photon is related to the momentum h over p. We use the same equation de Broglie did for the wavelength of a particle with mass, call it a massive particle, and we can just take that as h over p, and we use the formula for the momentum of a particle with mass. This is the relativistic formula, gamma mv. But in all these problems in chapter 29, these are going to be non-relativistic speeds, slow enough to where gamma is essentially equal to 1. We can just use the classical formula, momentum equals mass times velocity, or magnitude is mv. So let's go ahead and write that down. So the de Broglie wavelength of a matter wave, h over p, and p is going to be mv, classical expression, 1 kilometer per second. Sounds fast, but nowhere near the speed of light. So we need to go ahead and put these values in. So for h, I'm going to go look this up. In SI units, h is 6.626 times 10 to the minus 34th joules times seconds, divided by the mass of an electron. That's equal to 9.11. We looked this up. 10 to the minus 31st kilograms. And the speed here, 1 kilometer per second. Let's convert that to SI units. That's 1,000 meters per second. When we plug all this stuff in, we're going to come up with a value equal to 7.27 times 10 to the minus 7th meters. All those units are going to cancel out that and give us meters, since we're in SI units here. And this is what? This is like about 727 nanometers. So if this were a photon, this would be like in the infrared, right, barely out of the visible range. That's the wavelength of this electron. Now in part B, we're going to do the same thing for a proton. However, we weren't told the speed, we were told the kinetic energy of the proton. Well, we can still use the same formula. Gamma is equal to h over mv. And since we know what the energy is, it says 15 eV. If it just says a particle is a 15 eV particle, that means it's kinetic energy. We can use the classical equation for kinetic energy to solve for the speed, right? So in this case, we know Ke, that's equal to 1/2 mv squared. Let's solve for v here. 2 over m. Let's rearrange this a little bit, cancel some stuff out, right? So the v squared is equal to 2 times Ke divided by m. Let's take the square root of both sides. V in this case is equal to square root of 2 Ke over m. Now, so we can write this another way if we want. We could go ahead and plug the numbers and calculate v, or we can go substitute in for v. H over m times 1 over v, we need to flip this. 1 over v, since the square root is a power, we can go ahead and take the reciprocal of this, and it works just like this. And we can go ahead and multiply that over here. Now we can put our numbers in. So again, we got Planck's constant divided by the mass of a proton, 1.67 times 10 to the minus 27, multiplied by this square root. Again, we've got the mass over here. 1.67 times 10 to the minus 27, my units in there, divided by 2 times the energy, 15 eV. We need to convert that to SI units. We recall that 1 electron volt is 1.6 times 10 to the minus 19th joules. And now that whole thing, we need to square root that. Now when we go ahead and put that value into the calculator, this comes out to 7.4 times 10 to the minus 12th. And that's going to be in meters again.